we think about the biggest challenges facing the world today, we find that energy is ranked as the world's top problem. This figure indicates that the world energy demand is rising faster than current fossil fuel resources. As we approach 2050, the world's population pressure will increase, and the annual world energy demand is going to keep going up, and according to some other studies, it will double. Right now, we are faced with running out of petroleum and oil-based products, and we are dealing with the consequences of the side products they produce when they are used to make energy, such as the global warming. Today, we consume approximately 210 million barrels of oil equivalent per day, and all of them are from fossil fuels with almost no renewable resources. In the future, the ideal solution to our energy situation would be to use solar energy as it is renewable, sustainable, and clean. So we will stop combusting the hydrocarbon-based fuels or using nuclear materials to generate energy, and this will reduce pollution to a substantial level. The sun is very hot, about 5 or 6,000 degrees Celsius. That explains the fact that the peak of the emission lies within the visible spectrum. In addition, fully half of the sun energy lies in the infrared. This slide shows the daily and annual solar energy distribution throughout the world, as well as in Egypt in particular. It may come as a surprise to you to learn that the total amount of energy that reaches Earth every hour from the sun is sufficient to meet all the energy needs of the world for a year. Another way to look at this is if we were to cover approximately a quarter of Egypt's land with good solar cells, we could produce all the energy needs of the world. However, the reason why we don't fully use the solar energy resource is that we haven't yet found ways to make solar cells that are both efficient and cost effective. Opportunities for making more efficient solar cells can be found in making full use of the sun's broad spectrum. As you can see, this figure summarizes the basics of solar cells, how they work, and how they relate to the materials they are made of. A solar cell is a material that takes light and converts it to electricity. Solar cells are also known as photovoltaics, referring to photons of light and volts of electricity. Solar panels contain solar cells, which are most commonly made of layers of silicon, a semiconductor material made from sand. The semiconductor is a type of special material that does not conduct electricity unless excited electrons are present. When photons of light enter a solar cell, they get absorbed and excite electrons in the silicon layers, causing them to move and ultimately flow continuously through a circuit of wiring that feeds into the photovoltaic system. Harnessing the electron flow is what gives us electrical power. The first generation of solar cells is the conventional rigid silicon-based solar cells that have offered improvements in efficiency over time and reduction in cost, but not a disruptive change. The second generation of solar cells is the flexible silicon solar cells. Flexible solar cells offer the promise of significant cost reductions as a result of their ease of fabrication and installation, but the efficiency didn't improve over the first generation. The efficiency of the first and the second generations of silicon solar cells that you can buy today for your home or farm is around 10%. So neither the first generation of silicon solar cells nor the second generation flexible silicon solar cells has led to breakthrough improvements in efficiency combined with reductions in cost. Therefore, we still need to transform the current solar technologies into compelling, cost-effective technologies. The third generation of solar cells, developed by nanotechnology to improve efficiency, approached 30 to 40% efficiency to convert sunlight into electricity. Please note that it's easy to see why the point of efficiency is important until you think that it's not important to harvest every photon from the sun efficiently. After all, photons from the sun are free. But when you think about the fact that the cost of installing and maintaining solar cells, in addition to the area of space you are filling them into, then ultimately you need very much to think again about efficiency. Because if you don't achieve reasonably high efficiency from solar cells, you maybe will not be able to overcome the fixed costs of installation and the maintenance of solar cells. That's why the third generation of solar cells is envisioned to be a very big opportunity for the energy sector. Now, I will briefly discuss the most important third generation types of solar cells based on the current advances of nanoscience. First type is called textured silicon solar cells. Silicon is a good absorber of blue photons, the more energetic visible photons, but it gets much weaker in the absorption of light at longer wavelength. So we need to absorb all the light across the sun's spectral region that's above the visible light. With silicon, it's necessary to make a very thick wafer of semiconductor in order to absorb all the light in the infrared region because of the silicon's weak optical absorption in the infrared wavelengths. Historically, this has driven up the cost of silicon solar cells. Therefore, in textured silicon solar cells, we roughen the surface of the silicon solar cell to create the opportunity for multiple passes through this device. Instead of bouncing in and out of the solar cell and losing its chance for absorption, light is typically reacted or scattered in a different directions by the rough surface. This phenomenon in which light is trapped inside a semiconductor and given multiple opportunities to bounce around is called light trapping. And there are now low-cost and convenient methods to make nanostructured silicon surfaces that are prone to trapping light. Therefore, the third generation of nanotextured solar cells achieved lower cost and higher efficiency. Type number two is the plasmonics solar cells. Plasmonics are synthesized metal nanoparticles dispersed into paintable material, convenient to scatter and convey light in various directions, similar to light trapping technology. Plasmonics solar cells have a greater capacity to enhance the absorption of light using nanoscale interactions between light and metals. The third type is the Tandem solar cells. This type is a stacked solar cells made from several layers of different semiconductors grown on top of one another to allow better harvest of the visual portion of the sun's spectrum in a way that provide a good deal of voltage. However, tandem solar cells require costly ways to integrate the multiple semiconductors with one another. This costly type is used in concentrated photovoltaics, where optical methods are used to focus light from the sun onto a very small solar cells. Number four is the organic solar cells. The advantages of using an organic photovoltaics are to make cost-effective solar cells that are physically flexible and have extremely strong absorption and conduction of energy. Therefore, a very thin layer of these organic solar cells can achieve complete absorption of light. Number five is the colloidal quantum dot solar cells. In this type, the use of quantum dots semiconductor particles enable us to choose the targeted harvested light spectrum, whether visible or infrared, through the quantum size effects, and thus is advantage over the costly tandem solar cells. We can also change the quantum dots to quantum rods to enable the flow along their axis. Number six is the dye-sensitized solar cells. Those solar cells achieve light absorption using a dye, such as what you would find in food coloring. These molecules are very good at absorbing light, but on their own, they are not conductors. Therefore, the dyes must be put on a sponge of semiconductor that is good at transporting electrons, such as titanium dioxide or nanowire fingers. Seven, and the last type of solar cells I will discuss is the origami solar cells. The term origami was inspired from the ancient Japanese art of paper folding. The self-assembly technique of nanofabrication is used to fold the nanosheet materials into 3D structures by using capillary forces created by a water droplet. As you can see, the initial artificial flower-shaped silicon template was folded into a sphere using a water droplet. Unlike conventional flat solar cells, this spherical solar cell enhances light trapping and serves as an optical device, absorbing light from a wide range of incident angles. Nowadays, some of these exciting third generation nano solar cells are being commercialized, And some of their commercial applications benefit from the attractive properties of nanomaterials that are physically flexible. We can go beyond just thinking about installing these nano solar cells on rooftops, cars, or incorporating them into building materials to farm robots and equipment, sunglasses, computers, cell phones, windows, and many other devices capable of harvesting sunlight.